Well, as I say, representing data structures with invariants in Haskell, we will use BST and AVL as use cases. Okay? Well, data structures are typically defined by a series of invariants that the operators must preserve. Yeah? And this leads us to the question, can such invariants be automatically enforced by the language we usually use, in our case Haskell? Well, in functional languages like Haskell, we are able to ensure structural properties about the data. For example, we can ensure if that a tree is binary. But generally, we are not our languages are not expressive enough to encode at type level some semantic invariants. For example, if a sorted list is really sorted. Yeah, this is usually the work we do with dependently typed languages, not with Hindley-Milner languages. But since nowadays Haskell has introduced some extensions that don't provide proper dependently typed language programming, but do provide some kind of type-level programming, we have experimented on how to encode and enforce invariants at type level in Haskell using such features, using type-level programming. And we used BST, binary search trees, and AVL trees as case studies. So in this presentation, I will focus on BST, but then I will just try to talk just a bit about AVLs too. Yeah, we have followed three approaches on how to encode and verify environments, and they have somehow incremental rigorosity. The first approach, we call it fully externalist, in which we couple the structure with the proof of the invariant. Then we have another approach that is called internalist, in which we prove the preservation of the environment by each operation that modifies the structure. And then we have an internalist approach in where the invariants are encoding the data type of the structure. Yeah? But before diving into explaining the approach, we have to see how we can encode some information in the data types in order to be able to check those environments. Yeah. So as I say, we will use binary search trees as a case in this presentation. Binary search trees, I think everybody should know them. They are binary trees which have an ordering invariant. Yeah, and the ordering invariant is that every value in the left subtree has to be less than the value on the root of the tree, and every value in the right tree has to be greater than the value on the root of the tree, and this is recursive. Yeah. So usually in a language like Haskell, we encode those data types in a type like this, where we have like two constructors for the tree, one that allows us to construct an empty tree, another that allows us to construct a node with some value of type A in the root and subtree of type 3A and subtree of type 3F. Okay? Of course, this data type allows us to encode the structural invariant. Let's say, well, it has to be a binary tree. Yes, in this type we encode this, but we cannot enforce, for example, the ordering invariant. Yeah, and so to enforce the ordering invariant, we have to leave some more information about the data structure to the type level. And this is what we are going to do. Yeah, we're going to try to lift the information we need to encode such environments. In our case, we will assume that our trees contain key value pairs. Yeah, and that the keys are just naturals. This is just a simple way, a simple example of something that has some information we want to lift to a type level. That is the key, and is in this case the natural number, and some information we don't mind because it's not necessary to check the environments, the invariants, sorry. So we don't lift them. Yeah. So we define this key value type to represent the values we store in the tree. Yeah, and look that in this data type we have this type of kind not. Kind is a type of a type in Haskell. Yeah, so it's a type that is that can be a natural number, but we don't have any value of this type. Yeah, so this is what we call a phantom type. But we use it just to encode this information of the key at type level. And we will not, we won't need it at value level, so we will just only encode it at type level. Having this type, we also can define the type of trees which are indexed by trees, yes, at type level. And those trees are of kind tree nuts. Yeah, if you look at the constructors in here, for example, when we have the constructor for the empty indexed tree, we index this tree with an empty tree. And when we construct a tree with a key val and two subtrees, we index this new tree with a tree that is isomorphic to the tree we are building, yeah, but only stores the information of the keys. Yeah, so what we say here is that the keys are reflected at the type level in this structure that reflects also the keys and the shape of the structure. Yeah? So there we have all the information we need, yeah, at the types to be able to check if the invariants are satisfied. So for example, if we have a way to promote a number to the type level, this is example we can do with a proxy. Yeah, this in here we define a proxy value n0, that is just a proxy, and this proxy is of type 0. So we are like lifting the value 0 to type level. Yeah, and well, with this function we can construct a value key val saying which is the key and which is the value. Yeah. So we have this, we can, for example, construct this tree. Yeah, and this tree has this shape. And we can see that at type level, this is the type of the tree. This part is the type of the tree. This is the index that encodes this information. We are encoding the shape of the tree and also which are the keys for each element. Yeah. So in this picture you can see that the blue parts are the information that is stored at type level, and black parts are the information that is stored at value level. Yeah. So we have like a mirror, no? Like some of the information of what we have in the value level is also the kind level. And there's also here some information that since we don't need it at value level, we only have it at type level. Yeah. So now let's start with the approaches we have to check the invariance. The first one, which we call fully internalist. In the first one, we pair the structure with a proof that this structure satisfies the invariance. Yeah? So we define this type BST that to construct some value of this type, we will provide an indexed tree, sorry, with a tree T as index, and a proof term of type is BST indexed by the same tree. If we can construct, no, and this proof term will encode some inductive proof that the keys are correctly ordered. Yeah, the data type that defines this inductive proof just follows the shape of the tree and imposes some proof obligations in here. So put some constraints. Yeah, say, well, the ordering constraint of this invariant. Yeah, that this is a type family, that is a type level function. And this is a Boolean type family that says, well, all the values in the left subtree has to be less than the value n. No, and we impose that this has to be true. And this says, well, all the values in the right subtree are greater than the nodes in the value n. Yeah. This is the way we define this type family LTM, for example. And you can see that it's just the function here where we compare values and we just want to have those like less than, m less than n, and, well, recursively, we apply it to the subtrees. So, for example, now if we can define a proof term for this tree, then we can couple it in the tree, and then we are sure that the invariant is satisfied. Yeah, remember the type of our tree, of our example tree. For such tree, we can construct this proof, and once we couple them, this compiles and gives us the information that okay, this is a tree, this is a proper binary. Well, this is a proper binary search tree with respect to this invariant, this invariant. Yeah, and of course, if we provide a wrong tree or a wrong proof, then we get a compile time error. Yeah, and so if we can't construct a proof, or if we construct a proof that something that is wrong, we will get a compile time error. Something nice about using Haskell in this case and using type classes is that we can automate the derivation of proof terms using the instance resolution mechanism. Yeah, if we declare a class whose method is just a constructor of something of type is BST of a proof term, and then we declare the instances that put the proof obligations there. Then if the tree we are trying to prove as a BST tree, it complies with all those proof obligations, then we have for free the proof term, and we have the proof that the invariant is satisfied. Yeah? And again, if we apply it to an unordered tree, then this results in a compile time error because those instances won't apply to this tree because some of those constraints couldn't be solved, and then there won't be instances to make this for this type, and then we will have a compile time error. Looks nice. How do we implement functions for this structure? Since we have a lot of information at type level. Also, in this case, we have the key information at the type level. Well, we have to implement such functions with type classes. Yes, and the instances of such type classes are the functions equations. Yeah, for example, if we want to implement insertion in this BST, we will define this class insert BST, where we have to provide the way we want to insert at type level and the way we want to insert at value level. Yes, and they are coupled in this way. Yeah, because if we insert something of type KA in an indexed tree with index T, then we will produce an indexed tree with this shape, and this is as an associated type. Yeah, that is also some sort of function at the level of types. So we perform the insertion both at value and at type level. Yeah, when we insert, for example, in an empty tree, yeah, this is guided by the types, and we say, well, type level, inserting some k in an empty tree will generate an index or a type fork empty k empty. Inserting some key value in an empty tree, well, will generate this fork, yeah, with this empty tree with key value. Yes, and the shapes are isomorphic. Yeah. So we have like in some way to duplicate the code when we are doing this because we don't have proper dependent types. When we have to rely on some type level information, for example, when we have to, for example, to look at the keys and see in which direction we have to go to insert, Okay, then we can apply a type level function. For example, here we're applying this type level function compare nat that will compare the key and n. So those are types, but are types of calling nat. Yeah, it will produce a type O. And then we will delegate to another type class, yes, which will use this result. Yes, it will say, well, if you are less than, then I will do something. If you are greater than, then I do something, etc. Yeah. So this new helper type class, it's like the way we use to distinguish cases. Yeah, cases that are guided by type level information. Well, having those operations, then we can construct a type safe BST using this insert BST function. But look, we are constructed here an empty I3, and then we start to insert. Then we insert this complete structure, and then we try to make the BST. And at this point is when we will verify if the invariants are satisfied. Yeah. So with this approach, we are not checking if the insertion algorithm preserves the order invariant. We are only just like testing the results. Yeah. So we cannot say anything about the operations. Yeah, all the operations that we are defining. We are just looking at the complete structure we define. So trying to solve this, we experimented with this another approach that is what we call the externalist approach. In this approach, every operation that modifies the tree, we couple it with an explicit proof that this operation preserves the invariant. Yeah, and then look at, so for example, for insert, we will define this insert eBST function that given a tree that we know that is a BST, we will construct a new eBST using the same function that we used in the previous approach to insert, but now adding this proof that the BST will preserve the invariant. Yeah. So, and look that this. No, in here we should reuse the data types we defined for the full externalist approach, and we also reuse the operation. No, but we just add new operation that manipulates values of type eBST, that are the safe values, let's say, with respect to this environment. Yeah. How do you assure that this insertion function which preserves the invariant? Well, because here we use the associated type of the class we use it to define the insertion. Yeah, so when in this class proof is BST insert, which will produce the proof term that the new tree is also BST, takes well the key, the proof that the previous tree is a BST, and then will produce a proof that the key produces resulting of inserting BST using the insert operation we defined before is also a BST. Yeah, and this is information we had at type level. Yeah, because this insert function is the function we defined at type level before. Well, I won't go into a lot of into details here, but we can see that to implement the proof, we need to define instances, and we have to convince the type checker that such things are okay, and we are also using induction here. Yeah. So having this operation, now we can statically guarantee that on each step we are constructing a BST that preserves the invariant. Better. But since we are using type classes and we are using instances, it can be the case that we define the operation, we define the type class, and we omit some instances, and the fact that we omit those instances may not be noticed until we use this insert operation in some tree that needs this instance. Yes, in this case, we will have a type error as well. This instance is not defined, but otherwise, we are not really sure that the complete proof is done. Yeah. Going a bit further in rigorosity, we define this new approach, that is the internalist approach. Yes, and this approach where we mix everything together. Yeah, the type that defines the structure and the proof or obligations of the invariant. Yeah. So the invariants now are encoded into the tree type. For example, in this case is BST, and they have to be checked. So since they are here, they have to be checked any time that a value of such type is constructed. Yeah, look at here, we have the proof obligation that we had in the proof type, so that we had in the other approaches. So we can say here that values of that type are correct by constructor with respect to the invariant. Now, when we define an operation, for example, to insert something in this tree, we have like to put together, yeah, the algorithm of the insertion, let's say, and also the proof that the invariant is preserved. If you look at here, the code looks similar to both the code of the insert, which I showed before, and the code of insert preserves BST that I show later. Yeah, it's like a mixture of both. Yeah, because we have to do everything together here. So we are losing some modularity, but we are like anytime we treat a case of insertion, we also add the proof that this case of the insertion it's okay. Yeah. So we can say that in some way that this correctness proof is guiding the implementation of the operation. Yeah. So because we are implementing the operations of insertion or whatever algorithm we are doing on the instructor, but since we have to convince the checker that it's okay, that it preserves invariant, we are like guided by the proof. Well, this is the last approach. All the approach have a drawback that it's well, since we are putting a lot of constraints in there, the compile time verification increases type checking complexity, and compilation times grows exponentially in the size of the tree. Yeah. And also there are some runtime overhead because we have proof terms constructing there, and we're using type classes all the time and instance resolution. So it's this way, let's say, of being safe doesn't scale if we want to use it for big trees or big structures. We have to have in mind that this invariant checking, when we are defining in the last approach, we are defining we are trying to check that the invariant is preserved by the operations, is usually during the development of the operation. Once we have implemented those operations and we know that they satisfy them, then we can forget them. So what we try to do is to get like both the best of both worlds. Yeah, to have this safely when defining the operations, but then don't lose efficiency. And so to do that, we define it as systematic manual translation from invariant-based code to undecorated code. This is the usual code we will write to implement an AVL, and for example, a BST. Yeah? And in this translation, what we do is to remove all the type level information and remove all the proof term, basically. So how do we do that? Well, we start with a demotion phase, to say that is just to remove all this information that was promoted to type level. What I say, for example, oh, we had all this keys that now we need them at type level, well, let's just put them at value level. Yeah, so we will lose this type, we will put it in here, and we will lose this index. Yeah, so this is what we produce now, and this undecorated key value type. Yeah, with this NAT that now is at value level. We also remove some the decorations and prove obligations. So, for example, this I am explaining this the translation in the case of the internalist approach, but it can also be used to the externalist approach. In the full external approach, it has no sense because we have no proof of preservation, so we are not sure about the operations. So in the internalist approach, this type, which had the index that was the tree and has all those all those proof obligations, we will remove all of this, and we will end up with the usual way we represent a binary tree. Yeah. In the case of operations, it's also the other way around, as I said, we are doing. Yeah. Every class declaration we use to declare a function, well, we define them as proper functions. So class declarations are function signatures. Yeah, for example, in the case of insert, okay, we don't need now this information about how we do insert at type level. We only need information of how we do insert at value level. And we are, as I said, losing all this index information. So we end up with this signature. And all the instances we defined are now translated to equations in the function. Yeah, for example, this is the case of the empty tree, and this is the case of the insertion. Yeah, and then we end up with a complete implementation of insert, in this case, in a BST, which, okay, is not the usual one, but it's close to it, and we are kind of sure that it preserves invariant. Yeah. Well, we have done the same, we have applied the same methodology to AVLs, which are basically BST with a balanced condition. In the case of the externalist approach, since it is a bit more modular, it was just reusing the same types and adding a new condition that is that the tree is balanced. Yeah, but okay, we have to re-implement the operations because the operations in the AVLs are different than the operations in BST. And in the case of the internalist approach, we had to redefine everything because everything was tied together. So finally, to conclude, we have explored these three approaches for representing data structures with invariants in Haskell: the full externalist, the externalist, and the internalist approach. The externalist approaches promote modularity and enable code reuse across different representations of data structures. The full external approach is not does not give us guarantees about the operations. Yeah, it doesn't see that the operations preserve invariants. In the other way, in the other side of the spectrum, the internalist approach guarantees correctness by construction, but at the cost of reduced modularity. And well, as I said, the major drawback of all three approaches is that this exponential increase in completion time. But well, we showed a poor man of extracting code, let's say, a way of extracting code. That is this translation methodology. So I think this is everything I had to say. Thank you very much.
Don't mind if we could maybe skip the question section because we're sort of a little bit behind now on time. Jump into we can do questions offline, perhaps, on Discord. And then we can